Hello class and welcome to week 2. So this is again a review week. So I'm looking at material that we covered already in the previous course, EE2AD. But this is the last week for review. So starting next week we'll start new material. So today I'm looking at CMOS Digital Circuits chapter 13. Okay. And I'm sure some of you will at least remember that we've already covered this chapter and done a lot of problems and all that, but I think it'll benefit you by listening to me talk about it for a little while longer. So moving on to slide 2, there are 4 big sections in chapter 13 in our textbook. There's an introduction, and then 1, 2, 3. The first 3 are what I'll do today in 2 recordings, one the lecture and one the examples. And then this section 4, we'll do it in your next classes, one again theory and one problem. So we'll split this into 2 parts. 1, 2, 3 will be part A that we'll do today. Okay. So getting started, what is an inverter? I'm sure you know the answer to this because you must have studied logic in many other courses also, but obviously here we are more concerned with the actual circuit details and the device details, the NMOS and the CMOS devices. But let's start by looking at the high level at the logic stuff. So an inverter has a unity gain generally, and if there is an input A, then the output is shown with a bar, A bar, right? And you have this triangle and a little circle. Many times just a little circle is used to show an inverter or an inversion happening. Similarly on this side, from another book, A is where the input is showing voltage, X is where the output is and also showing voltage as V out, so V in, V out. Now a VTC, a voltage transfer characteristic, generally refers to the graphing between 2 voltages, right? Generally some input and some output. So in this case, the x-axis is the input, the y-axis is the output. So when the input is lower, which is here, the output is high. Similarly, when the input goes high, that means in this direction, the output drops to 0, right? So that's an ideal characteristic. Everything is nice and rectangular like this. Now we know we have studied a little bit of the VTC for both the BJT and the MOS devices, and the voltage transfer characteristic looks like it's it could be an inverter if you draw it like this and draw it like this. And we have generally focused on making sure we'll stay in the active mode here or the saturation here for amplification purposes. But for digital purposes, on off, we generally swing from cutoff to saturation here. And similarly here, we go from cutoff to triode when the input is high and when the input is low. Now there is a transition phase where you go from being high to low. In that phase, sometimes we'll enter saturation or active. But generally, when everything is stable and the input is high or the input is low, then the devices themselves are either off or in triode for CMOS. We don't do a whole lot of BJT switching stuff, BJT logic circuits. It's possible to do it, and they used to be done previously, but now almost everything digital has moved to CMOS. So I'm just going to focus on the MOS style digital circuits, logic circuits. Okay, so here's another example of the ITC. Now again, remember, I'm just trying to pick the important points from chapter 13. Certainly in 1 week we can only do so much. I think last time we did it in EE 280 we took 2 weeks for the whole chapter, so I can't go through all the details, and even with 2 weeks compared to all the material in the textbook, I can only deliver a small fraction of it. So again, I strongly recommend that you should read textbooks, our textbook preferably, at least once or twice. And if there are other textbooks that may help you, I'm sure even reading textbooks in the Chinese language also will help you. But again, make a habit of finding good textbooks and reading them, in addition to, of course, listening to me. So here's an ideal VTC again. As we had seen, it looks like this. We saw this on the first slide also. But here's a few other new things that we have identified, new levels. So for example, VOH is shown to be VDD. And VDD is generally the main bias battery voltage. VOL we are showing as 0. And again, the V input goes from 0 to VDD also. We also see something called VIL equals VIH equals VM equals half of VDD. So this is an ideal VTC, and we look at the definitions of these things like VIL, VIH in our next slide. So coming to slide 6, here's a more real VTC for a logic inverter. And here you'll see the definitions of all these voltage levels shown on the drawing. So VOL is output low level, VOH is output high level. VIL, which you see here, is the maximum value of the input interpreted by the inverter as a logic 0. So what that means is the input is along this axis, right? So the input, as long as it's up until VIL, so let's say this is 1 volt, right? So from 0 to 1, it still thinks that the input is a 0, as a logic 0, right? The actual voltage may be slightly more than 0. Now we know VDD, let's say VDD is, maybe 5 volts. Definitely VDD is considered high and 0 is considered low, but 0 to 1 also can be considered low by a inverter. So that limit, the higher limit, the maximum value of input that is still considered a 0, a logic 0, is called the VIL. Similarly, the VIH, that's the minimum value of input interpreted by the inverter as a logic 1. So as we go higher here, we hit VDD, for example, at this point. But let's say, which is, we said 5 volts, right? But let's say VIH is 4 volts. So even 4 is considered a high. It doesn't necessarily have to be only 5 VDD. It can even be slightly lower, like 4. And that is also considered a high as a logic 1 by the inverter. Okay. So VIL, VIH, make sure you understand the definitions. Then we look at NML and NMH. NML is called noise margin for low input, and that's this difference VIL minus VOL. So if this is 1 and that is 0, then it's 1. Similarly, NMH is the noise margin for high input, which is maybe VDD minus 4, 5 minus 4, also 1. So these noise margins are important. The higher the noise margin, the better, because that way, of course, not too much, but you want anything that looks like an low to be swept into the inverter, to be treated by the inverter as a low, right? And because circuits cannot be designed to always have exactly the voltages that you desire, like you might desire VDD 5 at a certain point, but you're only getting 4.7, 4.6 because of drops here and there. Similarly, on the low side, you're aiming for 0, but you're always getting 100 microvolts or 100 millivolts or something. So such small tolerances above and below the limits, also you want it to be useful, right, and not be rejected. So that's why having higher noise margins is considered a good thing. Okay, so VIL and VIH are defined as the VTC points at which the slope is minus 1 by 1. So another definition for VIL, VIH is a slope of minus 1. M is the point at which the inverter switches from one state to another, right? So we know that as the input goes high, the inverter has to go low. Then when the input goes low, the inverter has to change and switch to a high. So the point at which the inverter changes from low to high or from high to low, that is called the M point. Okay. And M is, it has two coordinates, the input voltage and the output voltage. Generally, you want them to be equal and so on. Optimum or best value of M and for the noise margins is VDD by 2. So the best for M, these noise margins, it should all be equal to VDD by 2. Okay. All right. Now let's look at some general information related to inverters, actual inverters being created or being, designed. So here, for example, you have a voltage controlled switch. So switch is closed when Vi is high. So off switch, infinite resistance. On switch, the resistance has an on resistance, R on. So when the input is low, is a totally open infinity resistance. When the switch is closed, you don't have zero resistance, but you have some R on resistance. And then the V output will be VDD times a drop across that on resistance, right? So such a circuit is called a voltage control switch. You have a double throw switch where the circuit operates like it's either in one position or in the other position. Here it's just open, right? Not connected anywhere. But here in both situations it's connected somewhere. And it can be in this circuit when Vi is high, and it can be in this circuit when Vi is low. So that's another example of an inverter being implemented. Lastly, we talk about two complementary switches. That means they kind of operate in opposite ways. So a pull-up switch works when the input is low. So when the input is low, the output is pulled up. to a high, which is how you want an inverter to be, right? But that portion of the circuit that pulls it up is called a PU network. Similarly, you can have a PD network which doesn't, so PU doesn't work when PD is working, and PD doesn't work when PU is working, right? Complementary. They only work when the other is not working. So when the input is high, the PD network pulls the output low. That's why it's called a pull down switch. Okay. Now they also have resistances. When the pull up switch is working, there's R on, and when the pull down switch is working, there's R on. But one thing that we say about these kind of double switches or complementary switches is that the static power dissipation is zero. That means when there is no action, there is no switching happening, then there is no power consumption. When switching happens during the transition from low to high or high to low, some power is consumed, but once the new state is reached, then there is no power being consumed. So that's the advantage. Okay. So MOS inverter implementation. Here is an implementation with just one device. Here's an implementation with two devices of the same type. So this is an NMOS, both NMOS. Here's our favorite inverter, CMOS, where both an NMOS and a CMOS device are paired, are working together. Okay. So these are practical ways in which inverters can be created using MOS technology. We move on to another important topic called power dissipation. So some power dissipation occurs even if the inverter is not switching, and this is known as static power dissipation. For CMOS, this is considered zero. For NMOS and other types, even during static, part of the static portion, maybe when the input is high or maybe when the input is low, it's possible that when everything is settled, power is still being consumed because some currents are flowing. But CMOS, once things are settled, no current flows, whether it's output high or output low. Hence, we say CMOS is a zero static power dissipation system. Okay. On the other hand, as the inverter switched from one state to another, current must flow through the switches to charge and discharge some specific load capacitances. These currents give rise to power dissipation in the switches, and that power dissipation is called dynamic power dissipation. Dynamic means when something is happening, when the changes are happening. So we've seen this before. When Vi is low, switch is open, no current flows, no power is dissipated. When Vi is high, switch is closed. So when Vi is low, switch is open, right? So when Vi is high, switch is closed, current flows from VDD to power ground, power is dissipated. So even during static, when Vi is high and output is low, current does flow from VDD to ground like this, so power is being dissipated. Static power is being dissipated. Again, CMOS, I don't want to say CMOS yet, but this complementary system dissipates no static power at all, only dynamic power when switching. Equivalent circuit when switching. When Vi is low, it looks like this, it's an RC. When Vi is high, also it's an RC, but now whatever was in the capacitor is flowing into the resistor. Here, Whatever is in the power comes from the battery, here power comes from the stored energy in the capacitor. Okay. So we have a few other terms to define. PDD is dynamic, is VDD times I. So that's the power being switched or consumed during dynamic switching. Another formula for P dynamic is F for frequency times capacitance times VDD square. And then the energy dissipated per cycle is CV square DDD or CVDD square. So we look at these in a little more detail, but for now, understand that power is an important concept in inverter circuits. Another important concept is delays, right? Propagation delay. Because nothing happens at infinite speed with zero time, right? All the switching does take time. So propagation delay is a result of the time needed to charge and discharge the various capacitances in the circuit. These include the MOSFET capacitances, the wiring capacitance, the input capacitance of all the logic gates driven by the inverter. So while we don't show capacitances so much, we just show the devices NP, NP, NP and just show some resistances. We think that's the end of it, but we know that anytime there are two terminals, there's likely to be capacitance. Even small wires with respect to ground have capacitances. So a lot of stray capacitances, little values, but they're all around and they all need to be charged and discharged. And that process takes time. So those times, RC time constants, right? So those times, they all add to the delay at which your circuit can work. And if you don't wait for the delays to complete, for the activity to complete, at the end of the certain time, the outputs you'll get will be meaningless. They'll all be, not what you expected. So having to take time into consideration, particularly delays, is a very important part of designing inverter circuits. So at the highest level, we can define something called TP, which is inverter propagation delay. And this TP is the average of two other TPs. One when the output is going low to high, that is, it's rising from being at 0 to the high value, and the other is when it's falling from being high to low. So for this fall or the rise to happen, a certain amount of time is consumed, and if you take the average of those two times, then what you get is called the inverter propagation delay TP. Now the maximum switching frequency is the opposite of this, the reciprocal of this TP. In fact, it's 1 by 2 TP, which is called 1 by T minimum. So the F maximum, that is the maximum switching frequency. That's why when you say a device like a computer has a 10 megahertz operating speed, or your memory stick can only operate at 20 megahertz per byte per 20 megabytes per second or something, all those speeds relate to how fast can you push various inverters and gates to do their function. and that depends on how well the circuit is designed, the natural properties of the semiconductor and all the wiring and the capacitances and all that. So the maximum switching frequency again depends on the propagation delay, which depends on a lot of the RCs present in the circuits. So what is TP low to high and TP high to low? It's shown here for a pulse. So VDD is being applied to a gate or an inverter. Then as the input goes from 0 to a high of VDD, we expect the output to fall, right? That's the inverter. It goes opposite. But on the rising edge of the input pulse, the falling begins. But it takes a certain amount of time for the falling to complete. And so we define TPHL as the time it takes for the output to fall from whatever peak value it was at, let's say VDD, to fall to half its original value. So VDD was 5 volts. At what time will it fall to half of 5 or 2.5 volts? That time, whatever picoseconds, nanoseconds it is called TPHL or high to low. Similarly, low to high is when the output rises from 0 to high or is trying to rise. So it goes from 0 to a certain high value, which is half the final high that it needs to get to, which is again VDD by 2. So going from 0 to VDD by 2 on the rising side is TP low to high. Okay. Alright. Here is another drawing talking about various other times. I think we have defined the TPHL, TPLH. Another time is T rise and T fall. And on the input side, also on the previous slide I showed you a perfect pulse with 0 rise time. But even that is not real. The input side also, the pulse gradually rises. So we talk about the input pulse's rise and fall time, which is defined as being 10% to 90% of the final value. So that gives rise to the output pulse, which goes from again high to low or low to high. And it has both TPHL and THL. Similarly, there's both TPLH and TLH. So high to low full time, which is from 90% to 10%, that's THL. TPHL is not the full time, but it's half the time. But the more important concept is the TPHL and the TPLH. Make sure you understand that very well, because we use a lot of those times in problems and other material. Okay, speaking of problems, there are some problems that we will come back to in a minute. Well, not in a minute, in my next recording. But let's move on. There's a couple more definitions. Something called power delay product and energy delay product. So we know power consumption is V into I, or it can also be written as FC VDD square for a RC circuit in terms of frequency and capacitance. So this is just the power, right? Dynamic power or static, total power. PDP just takes the PD and multiplies it by the propagation delay. So PDP is a figure of merit and is the product of power and time which gives it a units of energy. And you can compare two circuits without knowing too much to say how good one circuit is compared to the other for power consumption and speed, frequency of operation, by looking at the PDP. So if I tell you PDP is 10 while another one is 20, then you can say the 21 is better than the 10 one. So it's a figure of merit. So here are the formulas for PDP, two formulas. And also sometimes you are required to find the PDP at a certain switching speed, at a certain frequency f, or it's said just use the maximum possible frequency, which we saw as 1 by 2 TP, right? So at maximum possible frequency, the formula slightly modifies to half CV square dd instead of this formula. Similarly, there's another figure of merit called EDP, energy per transition, which has this formula. The same as this, but it's multiplied by TP. So we'll do some problems on this. For example, here is a problem, but we'll come back to this on slide 16 later. Okay, so after having studied inverters in general, and inverters can be made up of one NMOS device, two NMOS devices, NMOS, CMOS device, variety of options, right? But most of our work is focused on the CMOS inverter, primarily because of the advantage of low or zero static power consumption. So we have concluded that even though you have to put two devices every time, it's worth the expense. So at least for this chapter and what we are studying here, we will focus on CMOS. Later on we will come back and look at some advanced circuits where you can still use single transistor NMOS, PMOS and get some benefits. But for now we'll focus on the CMOS. Okay. So 13.2 is all about CMOS. Alright. So you've seen this drawing already. We didn't call it CMOS, but to implement this, obviously you need the CMOS. So we have two MOSFETs here, QN, which is N channel, NMOS, and QP, which is P channel. Roughly speaking, at the very high level, how do they operate? QN conducts this one when the signal at its gate is high. So the NMOS device, QN, is an active high device. That's one way to call it. Then the other device, the PMOS, conducts when the signal is at its gate is low. So the PMOS is an active low device. And when we say conducts, that means it's not cut off, right? It could be in saturation or triode, but at least it's not cut off. Okay? Alright. Another way that we talk about these devices when they work together like this, and this I found in another book. So there they use M1, M2 instead of Q1, QN, QP. But you can tell from the symbols that this is a QN, this is an NMOS, and this is a PMOS. So there is cooperation between the NMOS device and the PMOS device. So when Vin is low, M2 wishes to pull V out high. So when Vin is low, M2 says, oh, okay, I like this, so I want to make the output high. That means bring VDD down to V out. So it wants to turn on and do that. So at that time M1 says, okay, you do your job, I'll keep quiet and I'll turn off. So this is cut off. Similarly, when Vin is high, M1 does its thing, it closes, M2 is in cutoff, and because this is closed, whatever voltage was here already flows out like that because it's a short circuit. So V out goes to ground or zero. Okay, so that's one way to think about it, that there is cooperation between the two devices. So we talked about, and this is from chapter 5, we defined or we described briefly what CMOS is. We know that generally most devices, NMOS devices, are built on a p-type body. But to build a CMOS device, you still take a p-type body, but then you create an L-type bucket, a well, and then you add these p spots, and here of course you have the n spots, and then they are separated from each other by a thick section. So then you have source gate drain, drain gate source, and thus you have created on one body or one substrate a pair of complementary devices, NMOS and PMOS, and that is what we call CMOS. Okay, before we move ahead to study a little more about these circuits and what is going on between the two devices, again one more slide from chapter 5 I wanted to bring here. So this is called applying a small VDS, approximately 50 millivolts. So you know that for a MOS device to begin to work, first of all you need a channel to be induced, and that happens by applying a sufficient VGS, right? So if you look here, you have to apply first a voltage between VGS, right? Between the source and the gate, or the gate and the source. So once you apply that, a certain channel is created because electrons become free or holes become free to move, but they won't move by themselves yet. You need another voltage now between drain and source to be applied. Then the current starts to flow, right? It's a two-step process. So we studied all this in chapter 5 and 6 and the reviews. So as soon as you create a channel by applying a certain amount of gate to source voltage, which has to be greater than that VT, whether it's VTN or VTP, the VGS has to be greater than that small value. Only then will the channel be created. So once you are above that value, then the device, but only apply a small VDS. That means you are not going all the way to VOV, but you apply a small VDS, then the device behaves like a linear resistance RDS. So what is a linear resistance? It's not a fixed resistance. Its value changes with the applied voltage with VDS. Okay. Actually, I'm sorry. It depends on VGS, not VDS. But the resistance depend on, of course, the physical stuff, W by L, mu n CoC, but also VOV, which basically means how high or how much above the VT is the VGS, right? So those three factors define linear resistance, RDS, and it has formulas like this and this, they are the same thing. And then the current also in that stage can be shown to be like this. So these are important formulas and we use them here because when you see how a CMOS circuit actually operates, it's pretty complex And we've spent a lot of time on this. The textbook also describes a lot all these curves. But the basic facts to remember is the following. When the input is low, QP is on, and QP operates in the triode region as a resistor of value or DSP. So if you want to model this, look at this. So the QP can be shown with a little resistor or DSP, it's a low value, and QN is cut off, so it's an open like this. Okay. Similarly, when Vi is low, this is Vi is low. When Vi is high, QP is cut off, QN behaves like is on, right? It operates in the triode region as a resistor of value or DSN, right? So previously we called this DSP, this resistor. Here we call this DSN. So, and this switch is open. So you can see how the linear resistance property is being used to model the circuit operation of the two devices in a CMOS inverter. So here in this table 13.3, which summarizes a lot of information, you can see the values of this RDSN and RDSP. Okay. All right. So here are a lot of features of the inverter. And I think I've mentioned most of the important ones, so I'm not going to, I'll let you read it. You don't have to, I don't have to walk through every sentence. Let's move on to some other important concepts in the next 3 or 4 minutes. So, during the effort to understand what happens when input is low, when input is high, and then as the input goes from low to high or high to low, there is a certain process, right? The currents don't just wait for the inputs to go totally from one to the other, they also start to do their things. The devices are in a dynamic period for a very short time. So to understand all that, you first need to understand this concept of matched devices. So what is a matched CMOS pair? QN and QP are matched when their transistor transconductance parameters are made equal. That means if you take this whole thing is actually also called Kn, and this whole thing is called Kp. So Kn prime into omega by W by L of N, when it equals Kp prime of W by L P, the P side to the N device and P device, and these are related like this, the Kn prime, Kp prime. And we know mu n, the mobilities of n is much higher, it's about 2 to 4 times the mobility of P. That means mu n is 4 times mu P. And you need this to happen to be satisfied. L is generally kept the same, right? If you look at this drawing, L is the same for both devices. But W, this width is what is allowed to change. So to make Qn and Qp matched, the big rule is that Wp will be the 2 to 4 times of Wn. Whatever is the ratio given for mu n to mu p, that ratio is applied to this equation of Wp equals being higher in area than Wn. That means, higher in width. So the width of P region is 2 to 4 times the width of N region. Okay, so that is what is meant by matched. Now we like matched circuits or matched devices because it makes our job of modeling a VTC and understanding what is happening at various times in this drawing makes it much easier. So if the devices are matched, this looks nice like this. The trip point from where the inverter changes from one state to another is nice in the middle, and the trip point is exactly VDD by 2. So a lot of benefits come when the devices are matched. And it's easier to understand what's going on at the various regions. QN in saturation, QP in triode at this point, QN off here, etc. So there are a couple of drawings that help us understand what's going on in the middle. There are some equations for currents. We won't go through all this in detail, but when I come back, I'll stop now. We'll look at a few other things for matched, such as noise margins and all that, and then we'll also do some problems.